Okay, so I'm feeling a little bit unwell, so I'm going to move a little more slowly, which actually might be a good thing. But having said that, I'm still going to move fast. But remember, the idea is that you can pause this wherever you want, so you can pick me up, pause me, do whatever you want, and go at your own pace. Okay, so I'm going to start at 19 because I started at 18 and I realized it was going to take literally like 4 minutes to explain, so no thanks. I'm happy to talk about it if you want to come after school, whatever. Okay, 19. What are all horizontal asymptotes of the graph of this thing? Okay, we talked about this a little bit in class. Remember, the idea of horizontal asymptotes is we are interested in what is the limit of this thing, right, as x goes to infinity and also to negative infinity. So what I'm going to do is I'm going to stick it in infinity, and when I stick it in infinity, I feel like I've done this one already on video, but whatever, you can watch it again. It's 5 plus 2 to the infinity over 1 minus 2 to the infinity. Okay, 2 to the infinity is absolutely massive, so the 5 doesn't matter. Negative 2 to the infinity is absolutely massive, so the 1 doesn't matter. So this really becomes 2 to the infinity over negative 2 to the infinity, which is the same thing as negative 1. Boom. Okay, so that means as x goes to infinity, whatever the function is, it probably doesn't look like that, honestly, it's going to trend towards negative 1. Okay, but we also have to look at what happens when x goes to negative infinity. So I'm going to plug in negative infinity up here and see what happens. So I get 5 plus 2 to the negative infinity over 1 minus 2 to the negative infinity. Now something very different is going to happen here. All right, 2 to the negative infinity is the same as 1 over 2 to the infinity. 1 over 2 to the infinity, that's basically 0. So this is saying 5 plus 0, and 1 minus 2 to the negative infinity, that's 0. That's also 0. So this is really 5 over 1, which is 5. So now we know that this is 5, this is negative 1. The function is going to trend towards 5 in some ways. We go to negative infinity. Two horizontal asymptotes are negative 1 and 5. The lesson is for horizontal asymptotes, plug in both infinity and negative infinity and see what happens. Okay, let's keep going. All right, number 20. Let f be a function. Here's its second derivative. Okay, this is a nice one, looks like. What are the x-coordinates of the points of inflection? Okay, so this is what I'm afraid you might do. You might say, okay, so the second derivative is here. All right, an inflection point is where the second derivative is either 0 or it's undefined. Okay, so let me look. Oh, it's 0, 3, and 6. It's E. Now that might be the answer. I don't know, but we have to check. So what I would say is that the candidates, okay, the candidates are 0, 3, and 6. We're not sure if those are inflection points or not, but they're the candidates. That's when the second derivative could theoretically switch signs. So what we have to do is check, well, does it switch signs? So now we pick points, okay? So I'm going to pick negative 1, and I'm going to plug it into the second derivative. Okay, so when I plug negative 1 in, I get 1 times something negative times something else negative, so that's positive, okay? So it's concave up until 0. Now let's check what's going on between 0 and 3. I'll plug in 1. 1 times something negative times something negative. Wait, that's also positive, so it's positive again. Now I plug in something from here. I'll plug in 4, positive, positive, negative. That's negative. Now I'm going to plug in something big. Let me plug in like 10, positive, positive, positive. That's positive. Oh, there's really only one. I definitely messed it up. So this is what a great exercise. You get to see where I messed up. Oh, okay, so it switches positive to negative at 3, negative to positive at 6, so it's 3 and 6. I didn't mess up too badly. It's D. Okay, great. Let's have a look at the next one. Particle moves along a straight line. Great. The graph of the particle's position at time t is shown above for 0 to 6. The graph has horizontal tangents at t equals 1 and t equals 5, so I'm going to indicate that by doing that. And a point of inflection right there at t equals 2. For what values of t is the velocity of the particle increasing? All right, well, let's see. So this is its position. I want to know when the velocity is increasing. So let's think really clearly about this. This is the position, okay? The velocity is going to be the derivative of this. I want to know, hey, when is the velocity increasing, okay? The velocity will be increasing. Think carefully. When the derivative of the velocity is positive. Okay, this isn't velocity, this is position. So what that's really asking, and this is important, is the question boils down to this. When is the second derivative of this positive? Pause and think that through if you need to. So when's the second derivative positive? Well, that's when it's concave up from 0 to 2. Boom, hey, done. I have no idea why, but this is going directly to 25, which I'm going to skip because it takes a little while. So I'm going to look at 26 real quick. Arctan, you just need to know, so let's do this. What is the slope of the line tangent to this curve at the point at which x equals 1/4? This is basically checking, do you know what the derivative of this thing is? All right. So slope of the line tangent to the curve, you should know that that's derivative. So the derivative of arctan, you should know. I know this is one of those things that I probably should have had you memorize a little earlier in the year, but I didn't. So here, this is the derivative of arctan. Okay. So here's what I'm going to do. I'm going to say, all right, so the derivative of all this garbage, y prime equals 1 over 1 plus this thing here, 4x. Now it's a chain rule situation. We need to multiply the whole thing by 4, which ends up being 4 over 1 plus 4x. Okay, so there's our derivative. I want to know when x is 1/4, so I'm going to plug in 1/4. I'm going to get 4 over 2, which is 2, and it's a. Done. Okay. I'm not sure if I'm going to keep going or not. That's where 22 is. All right, so I'm going to briefly talk about 22. A rumor spreads among them. No, we did 22 in class. Forget it. All right, 23. Here we go. Which of the following is the solution to the differential equation given here, and they give us an initial condition? Okay, we did this in class, but it's very worth doing. You have to be able to solve differential equations, okay, especially with an initial condition. So I look at this and I say to myself, okay, differential equation, it's time for me to separate the variables, okay? I'm going to do two things at once. I'm going to multiply both sides by y and both sides by dx. Watch what happens. I get y dy equals x squared dx, okay? Once our variables are separated, we have to anti-differentiate. So I'm going to go ahead and do that. I get y squared over 2 equals x to the third over 3, and then don't forget your plus c. Okay, that's great. Once we have taken the antiderivative, at any point we can plug in our initial condition to get c. So I'm going to plug in 3 for x and negative 2 for y. See what happens. Plug in negative 2. This entire thing becomes 2 equals, I'm going to plug in 3 over here, 3, 9, 27. 27 thirds is 9. 2 plus c. Aha, c equals negative 7. Wonderful. So I know for a fact c is negative 7. I'm going to rewrite this. Y squared over 2 equals x, blah, 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 blah. All right, so that's that. All right, now I need to solve for y, basically. So I'm going to multiply both sides by 2. I'm going to get y squared equals 2x cubed over 3 minus 14. I'm going to take the square root of both sides. Y equals the square root of 2x cubed over 3 minus 14. Oh, awesome. The answer is D. This is a trap that the AP Calculus, the dragon who runs the AP Calculus test, actually that's a lie, I kind of like the test, likes to set. It looks like that's the answer, but we have to be careful. Okay, remember the square root can either be positive or negative, so we have to figure out, well, is it the positive one or is it the negative one? And what we do is we look at the initial condition, and we're like, oh, the y there is negative. Our y has to be negative too, so it's the negative version, which is E. Boom, done. All right, I think I have time for one more. All right, 24. Function f, if I can do it quickly, is twice differentiable. F of 2 equals 1, f prime of 2 equals 4, f double prime of 2 equals 3. What is the value of the approximation of f of 1.9 using a tangent line to the graph of f at x equals 2. Okay, so like I said, when we want an approximation using a tangent line, I usually try to get the equation of the tangent line. So here's what I'm going to do. I'm going to say to myself, all right, let's see. The derivative at 2 is 4. So I'm literally going to try to figure out what the equation of my tangent line is. So whatever, it's y minus y1 equals, oh, the slope is 4. You need to know the slope is from the derivative, x minus x1. Okay, so now I need a point. I need an x and I need a y. I got them from my from this little thing right here. I know x is 2, y is 1, so I'm going to plug that in. Y minus 1 equals 4 times x minus 2. Terrific. So this is literally the equation of the tangent line, which is great. So now I need to use this to estimate the value of y when x is 1.9. So I'm going to plug in 1.9. So y minus 1 equals 4 times 1.9 minus 2, and I will very quickly go through the algebra. So this becomes negative 0.1. Negative 0.1 times 4 is negative 0.4. I'm going to add 1 to both sides. Y equals 0.6. Boom, B. All right, so that I'm going to stop there. That was 9 minutes.